Okay, so to wrap up 16.5, we want to look at one other vector form for Green's theorem. Like we said at the end of the last video, the way we've been dealing with line integrals up until this point, the way that we derived them in vector form, we're looking at line integrals of the tangential component of f along C. So basically what that means is we've been looking at line integrals of this form. Line integral along C of f dot t ds, which you may remember this from 16.2, t being the unit tangent vector of the curve C. This wasn't really a useful representation of the line integral for evaluating line integrals, but it was kind of naturally what we landed on, the way that we derived them. And then we just put this into more useful forms. So again, that's because this is the unit tangent vector here, we refer to this as the line integral of the tangential component of f along C. The line integral of the normal component, the normal component of f along C is a line integral of this form. Line integral along C of f dot n ds. So we trade basically the unit tangent vector for the unit normal vector, specifically something that we call the outward unit normal, which points away from the region D. Trying to see how Green's theorem might relate to a line integral of this type. Let's take our curve C and suppose that we've parametrized it, so it's of the form x of t I plus y of t j. We can compute the unit tangent vector pretty easily. Remember, it's r prime over the magnitude of r prime, which in component form you would see looked like this. Okay, if that's the unit tangent vector, then the outward unit normal would look like this. Notice it's y prime of t over r prime minus x prime of t over r prime, a magnitude of r prime. You could derive this if you go back to chapter 13, the way that we come up with unit normal vectors. But an easier way of just verifying that this is definitely the unit normal is that it should be normal to the tangent vector. It should be orthogonal, rather, to the tangent vector. So if I took the dot product of this vector with this one, we would want it to equal 0. And it's fairly straightforward to see that that's what would happen. So this is what we're going to be using for n here. Okay, so what I want to do now is take a look at what this line integral looks like with this parametrization up here. So the line integral, and remember C is going to be a closed curve here surrounding a region D, because what we're trying to do is think of this in terms of Green's theorem, which concerns curves that are boundary curves of plane regions like this. Positively oriented as well. That's what the little circle here means. So again, line integral along C, f dot dn ds, would mean the same thing as this. Remember, ds is equal to r prime of t dt, so we make some substitutions here. F dot n would be a scalar field, so it's a function of t as well. And then evaluating this directly, we want to take the dot product of f, which is going to have components p and q. Okay, so maybe I should write that somewhere. F is equal to pi plus qj. Okay. So what would that look like? Well, the dot product of f with n is going to be p times y prime over r prime. That's this right here. Notice, because p is a function of two variables, x and y, and because we're going to be integrating with respect to t, I'm using my parametrization. X becomes x of t, y becomes y of t, and here's that product. Plus q times negative x prime over the magnitude of r prime. We get this right here. Okay, and then notice also the r prime of t that shows up naturally here when we convert our ds is going to cancel the r primes, the magnitudes of r primes in the denominator here. So after that cancellation, this is what I end up with. Now, look carefully at this. I have a y prime of t dt showing up right here. That is the same as dy. I also have x prime of t dt, that's dx. P of x of t, y of t can be written more compactly as just p. Q of x of t of y of t can be written more compactly as q. So this whole integral is written more compactly this way. And I'm looking at this, I'm realizing I didn't type one thing up here. C is going to be given by this parametrization, and we want to make sure that we make a note that t is going from a to b so that we can make sense of these limits of integration that are appearing here. Okay, now looking at this line integral right here, this looks very similar to what we see in Green's theorem. A couple of differences. I have a minus where I have a plus. Normally we would see the dx term first, but it would have been p dx plus q dy, and they've switched places. And then we have this minus here. What that's going to do is if we try to apply Green's theorem to this, the double integral ends up looking like this. The double integral over the region D of the partial of p with respect to x. Remember again, normally it's the partial of p with respect to y, and it's showing up over here. The minus that we normally get with Green's theorem is now a plus because we have the opposite here. So this is what my line integral looks like. However, my double integral after a value using Green's theorem on that line integral. This is the divergence of f. Now again, we've defined divergence to be the del operator dotted with our vector function and our vector field, and normally we've been thinking of the divergence of only with respect to vector fields in R3. But again, like we said before, you can take any vector field in R2 and think of it as a vector field in R3 by embedding it, which means add plus 0k here. Make a k component and just set it equal to 0. That would leave you with this as your divergence. Okay. So with that said, let's see. Now that means that this integrand matches the divergence of f. So I can just change this integrand into the divergence of f, and this gives me my line integral of f along C, or sorry, the line integral with the normal component of f along C. So in a sense, this is another way of representing Green's theorem. So again, I just want to recap real quick. We have these two different vector forms of Green's theorem. One makes use of the curl, and remember the curl is a vector field, but we can only take double integrals of scalar fields. That's why you need this dot k in here. Divergence is a scalar field, so we don't need to do anything extra, but we end up with the double integral of the divergence of f, and this is when you're doing the line integral along of the normal component of f along C. These are not brand new theorems. I just want to emphasize that. This and this are not brand new theorems in the sense that they come completely out of, or they're completely new material. They're just an alternative way of representing Green's theorem. All of this is still Green's theorem, but representing them in this way gives some useful interpretations that we will come across later on in chapter 16. So that's going to be it for 16.5.